This is the first slide. I'm going to review Shor's code and then continue with the rest of quantum error correction. Okay, so this is Shor's 9-qubit code, logical 0, expressed in terms of 9 physical qubits, logical 1 in terms of physical 9 qubit in this form. This was, as we explained, or at least from the point of view to understand, it's using a bit flip error code and then combined with a flip error code. So that expanded to 9 qubit. This is a 913 code. 9 is the number of physical qubit needed to encode 1 qubit. Code distance is 3. Okay, so we understand how this code can protect all 1 qubit error. Well, first, we consider the error that can be expanded in terms of Pauli matrices corresponding to general 1 qubit error. And we understand that the actions of this error is that the system is partly no error or partly a flip error on certain qubit. I didn't specify which one, just assuming there's some specific qubit, physical qubit. And there's also an error on Y error on that qubit, or it could be in the superposition of a phase flip error on that particular qubit. Okay, and we understand that by measuring the syndrome, comparing which physical qubit has flipped, by comparing pairwise the stabilizers, so we can, if we find that one particular qubit is flipped, then we collapse our physical state to this. If we find there's only one particular qubit has a phase flip, then it collapses to this state. Or you have both bit flip and phase flip, then it's collapsed to this one. And then from these, we know how to correct back to the original state psi. Okay, that's one way to understand that. The second way is to use the most general error correctable condition. P is the code space, for example, would be a projector onto 0 and 1 subspace. P is that projector. And we only consider the action of the code inside this. So the correctable condition is that if you have an error I and error J, you take this combination, project down to the code space. If you only have some arbitrary matrix multiplied by the projector code projector, then this is correctable. These errors, E, I, E, J, correctable. And we understood this by thinking that the error taking the code space to some other space, and these other spaces corresponding to different error are orthogonal. And this can be directly checked using Shor's code. I did one example, x1, x2, and show that they're all 0 or 1. So in some sense, it's independent of, so the coefficient, up to the coefficient, it's just proportional to the projector. That's the second way to understand Shor's error correction. The third way is using the stabilizer condition. And this is slightly more complicated. It requires the group theory. But it happened that Shor's can also be defined in terms of stabilizer. So for example, we understand that these are checking the bit flip error. I think this is checking phase flip error. They have stabilizer like this and stabilizer x1 to x6, x4 to x9. Okay, this is from bit flip. And then also the z1, z2. I think this is from phase flip. If we go back, these x check if you flip all these. So if you x1 to x6, if there is a minus sign, then this would give a minus. So the x would have a minus sign. So it's comparing whether there's a phase flip. Yeah. So this should be a typo. It's from phase flip. And these x1, z1, z2 is comparing the bit flip. Z1, Z2, for example, you compare Z1, Z2. If there's no flip, it's either 0, 0, 1, 1. Z1, Z2 would be just 1. So if there is a flip, then you have a minus sign. So this here, maybe I should correct that. Okay, but the upshot is that these are the stabilizers, at least the generator, the independent one, that when these operator apply to the code, it returns the code itself. So if you can measure the stabilizer, if you see a minus sign, that means you can determine the syndrome. Okay, but the condition for the error correction or correctable condition is that you involve the so-called normalizer group of the stabilizer group. Basically, that what I said is you take any element that commute with the stabilizer, any poly product of poly that commute with the stabilizer, and you want to take out the element that's already in the stabilizer. So that means in this Shor's example, the normalizer minus the stabilizer only contain product of 3 poly operator. The condition is that if this combination, that's also, we have that in the previous condition, EJ dagger EK, if that's not in this set, so then it's correctable. So we know that these are 1 qubit error. At most, these product can only have 2 non-trivial poly element, and these are 3, so definitely this is not in this set. Okay, but this require, using this method, it require you to find a normalizer group. It's a tedious process, but it's not that difficult. Just list all elements that commute with the stabilizer, as we did here. Okay. Okay. So let me just summarize quantum error correction. So it looks that there are more errors than bit flip and phase flip. However, also due to the superposition, this is from the first viewpoint. If you are able to correct some combination, you can correct all combinations. Okay. I want to say that quantum error correction has been well developed. There are also other new development, and some drawing really inspiration from classical coding theory, and has been applied beyond the quantum error correction itself to condensed matter physics, even string ADS-CFT, etc. So it's a field that's growing and has a lot of applications. And it's also related to, in particular, topological phases in condensed matter physics, which would be the subject of today. Yeah, so imagine you have a quantum computer that has quantum error correction capability. These computers would spend more time and more effort in correcting errors than your classical counterpart. Because classical counterpart, you only have bit flip error, and it's easy to correct those errors. So that's the summary. But probably the most important in quantum error correction is that even though we have errors in gate, in state preparation, in measurement, it is really important to know that if the error probability of these is less than some threshold, at least this threshold is non-zero, then you can actually, by using error correction, you can run arbitrary long circuit. Okay, so the idea is that, for example, we have Shor's error correcting code. We know that it can correct 1 qubit if the error is small. But if you want to run the circuit longer and longer, then the error would accumulate and there would be more error. The idea is that you do the second level of encoding. Each physical qubit is also an encoding, a 9-qubit encoding. That's a second layer. You could do a third layer, etc. And you consider the probability of error. For example, initially in the bare physical level, 1 qubit has an error P. If you do a 1 level of encoding, and we know that the error is reduced to a second order with some constant that need to be calculated. And if you have K layers, you can see that this reduction goes from the bare physical level P to P to the 2 to the K. And that means if P is smaller than C, then this would be decreasing. So basically just look at the bracket here. If this combination is smaller than 1, then the more layer, meaning the more power in the exponent, that means this number will become much smaller. So that means if the physical error is small enough, smaller than a certain threshold, then you can have a fault-tolerant quantum computing. So the threshold depends on error model, depends a lot of other, for example, connectivity, depends on the code, etc. It can range from 10 to the -4 to 10 to the -2. Okay. So that's probably the most important things in quantum error correction is that there is a finite threshold. As long as we can make our physical device to be of small error rate, smaller than the threshold, then we have a fault-tolerant quantum computation. So this is the work of many people, Shor, Aharonov, etc., that they contribute to this. Okay, so the focus of today's topic is on the topological code. So we talk about error correcting code. There are a few, or actually more and more, codes using feature related to topological phases of matter. So I'm just listing a few, but I'm going to concentrate on toric code to illustrate the idea. And this is related to topological phases. And there's an interesting effect about these topological phases is that there is some degeneracy in the ground state depending your manifold. For example, if you're on sphere, degeneracy, ground state, degeneracy is 1, and if you're on torus, the ground state degeneracy can be, for example, 4 in torical. I'm going to see that. And you can imagine if you put in more higher genus metaphor, there will be more degeneracy. And it is the degeneracy that we're going to encode our quantum information. So we're going to encode quantum information in degenerate ground space. Okay, we're going to see that in a few moments. And using these topological code, we don't need to do this so-called concatenation. This is concatenation. So we don't need to do many layers. Okay, but it also requires, as you can see, if it's on a metaphor, you may need to require a lot of qubit. So the most famous topological code, in my opinion, is the Kitaev's toric code. So Kitaev has a paper in 2003. There's also another paper by Wen in a slightly different way of the code. Basically, he's focused on the topological phases. So the setup is, you consider a torus, okay, a torus here. We can write in terms of a square lattice with periodic bounding condition. Basically, this goes back to the first side, and this one also goes back to the first side. So it's connected periodically like a torus. Okay, and qubits are on edges. Yeah, so qubit on edges, and there are operator acting on them. So in this case, there are 2 to the n square edges. So you have 2 to the n square number of qubits. So I've been saying that the ground space, so in order to define ground space, we need to define the Hamiltonian. Basically, this is the large matrix, so that the ground state will be the one that has the lowest eigenvalue. Okay, so the Hamiltonian is defined in terms of 2 types of operator. So one is called star operator. A star meaning that define the star, the center of star is on the vertex, and the operator acting on 4 neighboring qubit, like this one, 1, 2, 3, 4. So in a product way, so basically sigma x, sigma x, sigma x. So sometimes we use x. Okay, and the number of star operator is n squared, number of vertices in a square lattice. The other type of operator is called pocket operator. It's involving 4 qubits lying on the pocket. So the operator is product of sigma z. So z, 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 z. Okay, so, and these are translated through all the lattices. So you translate all the vertices, you have all the star operator. Translate pocket, you have all the pocket operator. So the Hamiltonian is sum of these two, and put a minus sign because then you can define the ground space. The ground state would satisfy this. Ground state. Okay, so that means this actually defines the stabilizer group, right? So remember, this is our stabilizer operator, and they commute. That's necessary to define the stabilizer group. Okay. So one question you can ask is how many qubits we can encode. So basically, it counts how many independent stabilizer generator. Okay. So to count that, we need to see whether there's any constraint on these star and pocket operator. So recall that on each vertex you have a star operator. If you consider product of these on all the vertices, then neighboring that would cancel the overlapping edges. And if you consider fitting all the stars on all the vertices, it would be a product of that becomes identity. And similarly for the pocket, you consider putting pocket on all, putting these on all the pockets. So the Z and Z would square to identity. So there are two constraints. Previously we have two star plus pocket operator, 2 to the n square one, two constraint. And number of qubit is 2n squared, so there are actually 4 degeneracy. So this is number of qubit. Number of logical qubit equal to the physical qubit subtracted by generator. Yeah? Question?
Why there are two constraints?
As I said here, right? Product of BP equal to 1 and product of AS equal to 1. These are the two constraints.
Okay.
So you can consider this, I put this on a torus. You could also consider putting in a manifold with more holes. And this is also denoted as genus G. This is the number of qubit is on the edges, right? And number of vertices plus number of phases. These are the sum of star and pocket operator. Two constraints because product of all these, just like this. And you can see that this is 2G, number of qubits. So the degeneracy is 2 to the 2G. That's 4G. Okay. So on this torical, on the torus, that's why it's called torical. So torus, you have only 2 logical qubits that you can encode. Okay. So I want to mention that so in some sense there are 4 degenerate ground states, and separate with that there's a gap, a finite energy gap. Okay. So yeah, so this is just a reminder. We talk about the stabilizer group logical space. Basically what I was saying the previous slide, previous two, I was just using that. So you have a stabilizer group. These are the generator, n minus k generator. And if you have n qubit, these are independent constraints. Each stabilizer generator provide one constraint. You have n qubit minus the n minus k constraint. You're left with 2 to the k vector space, which is effectively a k qubit subspace. So this means that we can have k logical qubit operator, logical x and logical z, and all these need to commute with stabilizer S. And okay, that's here. And they need to form logical operator. So for the same qubit, same logical qubit operator, they anti-commute. For different logical qubit, their z and x, they commute. Logical qubit. Okay. So that means we should apply this to the toric and find what are the logical operators. Okay. So it turns out, in order to satisfy the commutation, the commuting with all the stabilizer elements, for example, the star operator, there are star operator on all lattice sites. There are pocket operator on all the pocket. So in order to commute with these operator, you need to form actually a large circle for these operator. For example, what I listed here, CX1 that cross these edges, it basically means that this is a product of X on these edges. Let me just say product of X on edges cut by CX1 curve line. Okay, you can see that it would commute with all the star operator because this is just X, so X commute with X. But if you have pocket operator, each pocket that that have overlap with this line would overlap at 2 locations. Okay, and for this pocket, it does not have any overlap. So the C product of these all X looping around the torus. So for example, it could be like these, looping around the torus, commute with all the stabilizer. Okay, you could also do it on the other direction, product of X. Okay, you could also have the Z operator on the line of these. I label as C, Z1, so these are Z, Z, Z. Okay, and you could also have another CZ2. So the subscript 1 and 2 basically indicate the logical qubit. So the logical X and logical Z need to anti-commute. So logical X for the qubit 1 is this line. Logical Z is that they intersect at this location. For the CX, it has an X on that. For the CZ1, it has a Z on that, and they anti-commute. And similarly for the other CX2 and CZ2, okay? So basically that explains the notation here. Logical qubit 1 or 2. Z operator is defined as product of these Z's on the corresponding line. Okay, the CZ1 is this horizontal orange line. CZ2 are these vertical orange line. So product of these Z operator on this line define a logical Z operator. A product of X on these red curve, those cross the edges that define the logical X operator. Okay. Yeah, so we already checked they commute with the star and pocket operator, and they cannot be generated by the star operator nor the pocket operator, right? Yeah, because if you consider product of pocket operator, these overlapping edges cancel, so it becomes a loop. You try to form a bigger loop, it can wrap around, but actually wrap around twice. So wrapping only once, the loop is not generated by these stabilizer. So these are really independent of the stabilizer element. Okay, and indeed satisfy they are logical operator. These anti-commute because they cross at one location. Okay. And because they commute with the stabilizer, right? And so they are the action on the ground state. So for example, action on the ground state, because it commute with the stabilizer, right? So the action on this is ground state. So it has energy E0. Yeah, that means that the Hamiltonian acting on this is also a ground state. This is also a ground state. This basically means Xi G is a ground state as well. Okay. And notice that here, this curve, even though I draw a straight line crossing that, you could actually deform. So let me see if I could change the color. Show the pen. Okay, it's hard to change color.
I thought there was in color below.
Where? Right? Oh yeah, in color. Yeah, but thanks. Let me change the blue. So we define these, for example, cutting across these edges, CX2, you could actually deform it. If you consider this one, let me use, yeah, let me just draw. I deform in a way that I can just go up and horizontally and coming down. This is also a valid loop that commute with all the stabilizer because each blockade is they're still cutting only even number, right? Even number. You can clearly verify that. Okay, so that means this is also a valid operator. And indeed, you can see that the additional thing can be canceled out. This curve and that curve can be deformed by putting the star operator here. Right, the star operator would sort of move this curve around. And because these star operator, they are stabilizer, they don't change the code space. So what I'm saying is if you have a logical operator, and times any stabilizer operator, they are equivalent. Logical L is the same as logical L times the stabilizer, because S acting on ground state does not change. Okay, but the Xi acting on the ground state can change to a different ground state because there are 4 of them. So maybe what we could we would discuss the other 4 ground state, but let me talk about excitations first. Suppose you have a ground state. So how do you create excitation? So the ground state, they are stabilized by these star operator. So that means you can treat these AS and BP as a number. It's 1 in the ground state. This means ground state has this energy. To create excitation, you could just, for example, apply a X. If I apply X, a single X. So if I apply a single X, it commute with AS, the star operator, but anti-commute with 2 pocket operator. So the 2 pocket operator are on this side and that side. Okay, you see that the vertical, yeah, so it creates a minus sign here and a minus sign here. Okay, So that's indicated here. These shaded blue minus 1. So I here indicated there is a pair, but if you apply another x here, that would cancel out this -1, and the other -1 will be move around. So that's why it's, if you use x, can move the excitation around. Okay, and similarly, if you apply z, it anti-commute with the star operator, so we create excitation indicated on these vertices, the circle here, and the other end is here. Sometimes we give them a name, we call it charge because it's on the vertex, it's like a charge. And these are on a pocket, it looks like a flux, so like a flux through some pocket. Okay, so charge on the vertex. Okay. And so these breaks A or B equal to 1, for example, one of them is -1. However, they come in pair because the constraint that they product to 1, right? If this is -1, you need to have another -1 to cancel that out. So they always come in pair. So each pair, you get a minus sign, another minus sign, so it's -2. So there is energy for difference, okay? Because you are taking the +1 to -1, +1 to -1. So overall there's -4 and this minus sign, overall minus sign. Okay, so the energy excitation has energy for a pair excitation. Okay. Okay. And how do we correct the error? So for example, we see that this example has a pair of -1 plaquette. These are caused by the X errors, right? A string connecting the two plaquettes. How do we correct that? If we can measure these stabilizers, because they are, these all commute, so you can imagine you can measure these observable. If I find there's a -1 here, -1 here, then it's likely that there is a string connecting this. You might as well use the other string, it's also okay. Because if you apply an X to this, a string of X on these three edges, it would cancel out, but if you apply on the lower branch, it will also cancel out. The only cases that it will not cancel out is if you try to loop around, that will not cancel out. So this, applying this will not apply correction like this. That wrap around will not correct the error. Instead, it would cause some logical bit flip. Okay. So we also see here, in order to make the error that uncorrectable, you need to sort of span the whole size of the system, the linear size of the systems. Indeed, that's what the logical operator are doing, right? So we have seen the logical operator, they are curved that wrap around. Okay. So basically the upshot is that you identify the local pair of charges. It doesn't matter how you identify the pair. As long as the rate is low, these pairs should not go very far. Okay, and you just locally correct them back. Okay, so that's the way to correct local errors. But if you see the unlikely event that the error sort of spanned the whole size, and this cannot be corrected. because we don't know it's a lot. We cannot detect. Yeah, because for this particular example, it's a logical operation. But if you have error that almost span like this, then -1 is here. If you incorrectly identify as this closest distance to correct that, then it would connect to become a logical operation. Okay, but these long distance error, long distance string is unlikely because assuming error rate is small enough. Okay. Yeah. So the next one actually is the error correction condition. So how do we know it's error correctable? We can apply, for example, these the original definition of correctable condition. So this can be easily seen because the torical is projectors onto the P is the projector onto the ground space, and you can easily check that any expectation value of ground state and local operator so for different ground space, different ground states. So let me use a different ground state 1, let's say ground state 2. They will be the same. Otherwise, using the notion of topological phase, then you'll be able to detect these degenerate ground states using local operator. Okay, this can be made rigorous because you see that these E dagger E, they need to be wrapped around in order for this to be not whole. Okay. So you can easily check for local operator if these are local. You will see that these are actually 0. Okay. So the other way to see that that this is an error correction code correcting one error is that you check whether these combinational error is not in the normalizer minus the stabilizer. But we see that the normalizer, these are the set of operators that commute with stabilizer, and you want to remove the stabilizer element himself. So the only thing that are possible are logical operator or logical operator times, the local stabilizer. So these can only be logical operator, and they wrap around. So they need to wrap around. But our local error, 1 qubit error, for example, they don't wrap around the torus. Okay, so in fact, this does not just correct one qubit error, it correct all the errors that happen in the region and next region, as long as the combined region, they do not wrap around. As long as they stay local, then that can be corrected. Okay, any question? Okay, so next I want to talk about
exact ground state.
Yeah, so that's what I'm going to write down. So we're going to construct the ground state. And there are 4, so let's first get one and then see if we can get the other. So how do we construct that? So first, we need to satisfy the pocket operator and the star operator. So to begin with, I choose all zeros. These satisfy the BP because BP apply to the 0 will still return the 0 because Z acting on 0 is plus 1 times 0, right? So then we need to see if we can satisfy the AS. And AS, they locally flip, for example, as shown here, they locally flip 0 to 1, right? And they flip in this pocket sense. Sorry, in the star operator sense. Yeah, but the star operator, if you want, it's a pocket and a dual lattice. So basically, it's flipping 0 to 1. So how do we make some combination so that this ground state would be satisfied? Right. So we have 0 as one configuration. The idea is that why don't we add all other combination flipped by AS and just add them to the state. So basically, this is the initial state, and this is flipping by AS or product of AS. So that's why I call this is a group generated by AS, and you probably normalize, okay? So that would satisfy the AS because one AS acting on this can be absorbed. So for example, AS and G is another G prime. So that means this is stabilized by AS operator, okay? Okay, so this seems to be really algebraic construction, but there's also a graphical way to understand that. So if I just regard my 0, 0 as vacuum, meaning nothing, so on each edge there's nothing, and if I flip to 1, then I would try to write a symbol as a loop to indicating those that has 1, like 1, 1, 1, 1 here. If I have neighboring two G multiplied together, then actually I create a bigger loop. So for example, there's one like this. These are maybe bigger loop, etc. Maybe some other small loop, etc. So the ground state G00 that I denoted is really equal superposition of all possible loops, and these loops are contractible. Remember, we talked about that we cannot form a big circle using just the stabilizer operator. So there are some of all possible configuration of ones that form loops. Okay, so that's the intuitive understanding of this exact ground state. What about other states? There are 4. What about the other 3? And remember, we already have the logical operator, and we can basically flip them by using this logical X operator. So the 2 qubit I denote 0, 0, right? And I flip them according to the X loop, X1 loop, or X2 loop. These will flip the corresponding to two corresponding qubits. Okay, you can check that. You can check first. In order to do this, actually, you should check the Z1, logical Z1 and logical Z2 acting on my 0, 0 should be +1. Okay. Indeed, this can be the case because Z are product of these Z here, right? They commute with all these stabilizer. So if we bring all the z to the right-hand side, they act on 0, we'll just give you a plus sign. Okay? So that's how we get the other 3 ground states. Okay. And we also have a pictorial understanding of the other ground state. So G00 is superposition of all parts of loop configuration, contractible one. Now, if you consider, for example, X2, which actually is obtained from multiplying this G00 by these non-contractible product of X, that means it would flip, right? So I think I should have an example. Yeah. For example, this would flip. This would flip the loop to that, right? So initially there was no, there was only the contractible loop. But if you flip this to 1, 1, 1, 1, 1, and this becomes 0 and 1, so it becomes a loop like that. So that's this loop. Okay, and it becomes non-contractible. So the winding number in this direction is 1. Okay, and you can actually do that on the other. If you apply the logical x1 here, you would have winding number 1 and this vertical direction. Okay, so these 4 different loops, you can understand them as a product of loops with, for example, winding number depending on the logical state. So if it's 0, then 0, the first 0 is winding number in this direction. Second 0 is winding number in this direction. Okay. Any questions so far?
Yeah. So why x square is logic?
X squared is what?
Is equals to nothing. That is
X,
2, yeah. X logical x, we apply logical.
X squared is identity.
Yeah,
right?
and we apply logical x twice, so we have 2 winding loops.
No, so we apply the logical X on the first qubit. This is a logical X on the second qubit.
No, I mean if we apply the same logical x.
Yeah, then it's identity if you apply it twice.
But we can also have 2 winding loops. How do we identify?
Oh, but there's only even and odd, right? I mean, how do you count? I mean, this will be that, and that's just one winding number.
Yeah. So, but if we apply x twice, then we have 2 winding now.
No, it would just flip that back, right? So if you apply 1, you apply x2,
yeah.
You apply x2 again, you take it back.
Yeah,
right?
but
If you look at the configuration.
If we apply x2 in another place,
yeah, so that would
2 loops. We should
no, yes. So if you apply to other places, let's say I apply here, right? Okay, if I apply here, right? So I apply here, x, x, right? So I would have contractible loop. I would have contractible loop. These would contract, right? So you have contractible loop, and that would contract to this. You see that? And so it will be just no winding number. So as I said, because these x, they can be deformed. So this is equivalent to that. So apply here and there, they are the same. So that means apply twice, it go back to itself. Maybe you need to think about it more if you don't get immediately. Okay. So we talk about excitations, I introduced charge, flux, right? There's actually a third excitation, and we can also consider exchange between these excitations. So first, exchange between these excitations give +1. So same type of charge or flux. So we also call these anion. Same type of anion. They look like boson, but there is a third type. Okay, maybe before I introduce the third type, let me talk about the braiding of E around M. So for example, this is a pair of M, a pair of E. So it could be from the right-hand side, just move it around. And then I move this E around. How do I do that? I just apply the Z operator. Right? So apply Z, 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 Z. I apply Z operator and then take it back. But there is a red dashed line between the two M, and these has X operator. So there's a X operator, X operator, X operator, and these anti-commute. So braiding of E around M or vice versa give a -1 sign. Yeah, so basically that is due to the anti-commutation of X and Z operator. Okay. Yeah, so I mentioned that there is a third anion, non-trivial anion. Of course, there's a vacuum. Vacuum there's nothing. You have a charge, you have flux. There's also a fermion. A fermion is a bound state of E and M. What I mean is you treat E and M as an object. So for example, there is a pair of E and M here. So this is the pair of fermion. Okay, call this F. But you might want to see the statistic by looping this around, right? But this is really looping around a fermion. If you have take a fermion and you exchange them twice, you don't see the minus sign. It's still plus sign if it's a fermion, okay? So there's also a question, how do we see the statistics? So I'll get to that later, but let's talk about E and M. In the language of anion, they fuse to M, they fuse to F. So E times M, they fuse to F. If you take another E and fuse the fermion together, it would cancel out the E and return the M itself. So basically this says E times E is identity. I should have that in the next, yeah. Okay, I did not have. Okay, if you bring two E together, it will fuse to identity. So remember our E is created from vacuum by a pair. So if you bring them together, they will annihilate them. Okay.
So what is F?
F is the bound state. F is E times F times M. F is the bound state of E and M. They should move together. Okay. And I say that the braiding this around give plus sign, but I claim that it's a fermion. So how do I see the fermion? So how do I see that? I need to just exchange, right? I need to just exchange. So if I loop around, then it's not the same as exchange. To explain the fermion or the cell statistics, it requires a slightly more advanced subject. We talk about the qubit basis. So maybe this is logical. Yeah, already said it. Logical basis. It's just flipping using logical operator. as a logical basis. There is also another basis we can use. It's actually, in some sense, a plus minus one basis. In this case, it's a mixed basis. Mixed basis. And this one is called a topological charge basis. Basically, if you take this two line, CX2 and CZ1, you can define eigenstates, simultaneous eigenstates of Z1 product X2. If you define that, you find that these states are just combinations. Really just plus minus sign, just meaning that this is plus minus, really just a plus minus combination. It really just like a 2 qubit. Usually when you write 2 qubit 0 and plus, it's really just 0, 0 plus 0, 1, right? So it's really similar to that, but this basis has an fixed eigenvalue, right? Fixed. So in some sense, as a fixed topological charge, it looks like there is a anion, the thread to this. So remember that using X, I create a plaquette, or I create flux. Using Z, that I create a charge. So it looks like there is a sort of anion flux threading that, okay? And then we can consider a rotation by 90 degrees. So if you rotate 90 degrees, so the effect is that the loop, vertical loop become a horizontal loop. And in some sense, this means that these strings get rotate. So our previously logical basis state is transformed like this. So it's like a swap operation in our logical subspace. And this is indeed a swap, right? You have seen this swap operator, okay? So in terms of the charge basis, which really just a combination, linear combination, you can transform, really just transform to 0, 1, plus minus basis. You see that there is a matrix like that. This basically is a braiding statistics. For example, this might be vacuum, charge, flux, fermion. If you take a E and, sorry, this is identity, E, M. If you take an identity, sorry, you take an E and exchange loop around with, so you braid around E and M, there's a minus sign. This is what we demonstrated earlier. So you take a fermion that braid with an M and get a minus sign. So this matrix, the so-called modular S matrix, give further information about the braiding. So basically take a particle and braid around, okay? But this does not give us the fermion. The fermion braid around still give a plus sign. So in order to get the so-called self-statistics, we need to consider something else. So at the moment, we consider only mutual statistic, which is just braid around. But in order to see the self-statistic, we need to sort of exchange. We can only do half of the rate. So this actually is related to something called Dehn twist. A Dehn twist is something quite easy to understand. If you imagine cut this, you cut this, and then you twist this by one cycle, 360 degree. So you cut in half and then twist. You see that in one direction, it was wrapping around like this. But if you do that, then the winding would also involve in the other direction. And it's not difficult to see that, for example, the winding in this direction will be added to the other direction. So like this. So it was here, and then it adds the other direction winding. So there's a vertical direction, and this is the so-called modular T matrix. It looks like a C0 gate in our logical basis. But in the topological charge basis, you see that there's a minus sign. So all the others are boson-like, like cell boson. But this is a cell fermion. Okay, so this gives you the exchange statistics, cell exchange statistics. So the minus sign, this is how we get the minus sign. Okay. So I think this I illustrate with example, but there's a deep theory behind this. But I think the torical is the simplest case we can use explicit example to write all these. So there are like mathematics, modular transformation. It basically is just changing your coordinate. It can be rotation and the so-called SL2Z group, special linear, 2 is 2 by 2, Z is if you only use integer coefficient. But basically the upshot is that it's a combination of rotation and the Dehn twist. Okay, Dehn twist, you can also regard that as a shear. It's basically shear. So also shear. And then you just move this back to that. Okay, so there is more general theory behind that. And it says that if you use these topological bases, the rotation give you mutual statistics. It's like you create, maybe it may be bigger. You create from the vacuum a pair of beta anion, a pair of alpha beta anion, and you just braid around. And here you create, for the T, you create from vacuum that same alpha particle, and they just exchange. It's not a whole loop, it's just half. So this would give you a self-statistics. There's more general theory behind this, but we use the torical to illustrate the simplest. So I want to pause to see if you have any question. Okay, so maybe I just go back a little bit. So we start with a model and we construct a logical operator, and we find that there are excitation that you can characterize as charge, flux. They are really created by the simple X and Z operator. And you can imagine braiding these around. Braiding is really just applying, for example, applying operator Z, and then that would drag the excitation for a whole loop. It comes back to your original configuration, but there is a minus sign. This is the mutual statistics. But to get the self-statistics, we need to do a little bit further. to consider the Dehn twist. And there we have to introduce these topological charge bases. Although this is an advanced topic, but the idea is really simple in terms of, if you use in terms of a basis change. We were using 0, 1 basis, now we use 0, 1 and plus minus mixed basis. But the physical meaning is that there is a fixed quantum number in one direction, sort of as if there were some anion threading here. So when you do the Dehn twist, it's like moving a particle and wind around. Okay, so that's the meaning of these. And 90 degree is really just doing a braiding. So that's the meaning of these. If you don't get the general idea, at least you can understand the specific example. Okay, and we talk about the error correction, correctable condition. So I want to also mention there are other topological error codes and won't have time to talk about. There's also something called surface code. Surface code is really a toric code on the surface with boundary. You could have the so-called smooth boundary like that. You could also have rough boundary. And the definition is really just still using AS and BP. You may ask, why do we want to do that? Because in reality, we may not have a torus that we can engineer for the qubit, but it might be useful to consider just planar geometry. And to do the qubit encoding, then we cannot use the big circle. We would punch hole. So punch hole. And a pair of hole would encode logical qubit. Okay. They also so that actually is one that the surface code is what Google is aiming at. Google is aiming to implement surface code. For quantum computation. Maybe one day you will hear the news if they succeed. There's also other topological code. For example, the color code. I don't want to talk about the detail, but the qubit in this case, they are lying on the vertices, and they're different color representing different stabilizer colors. There's also something called subsystem code. In one particular example is this Bacon-Shor code. I also don't have time to explain. Perhaps a more interesting recent development is this fracton code. These are defined on 3D. What I've listed here are two stabilizers, and it turns out the logical operator have some fractal structure. That's very interesting. But again, I don't think I have time to talk about this here. But I want to mention that for the current quantum computation, we still are not able to implement quantum error correction. Well, except there's some new development. Maybe I think I post that in the course website. Actually, there is a recent 9-qubit implementation of Bacon-Shor code using, I think, trap ions in Chris Monroe's group. So that is actually a big achievement because they were able to encode so that after encoding the error is reduced. Okay. So, but I want to say that in general, we still do not have an error correction that can be implemented together with quantum computation. So there are some idea of, for the near-term quantum computer, what we could do is maybe do something called error mitigation. This is not active error correction. The idea is that if you create a gate, you're applying some field, some maybe magnetic field, and the area, if you have same area, it's representing the same gate. So ideally, so as I show here, different color, they have different, although the stretch is, the length is different, but the area is the same, they're representing the same gate. But there are some, if there's some error that occur, because for example, this one has a longer stretch, so experience more error. At least the rate, the cumulative rate is larger, so this low error, lower error. So the idea is that if we have, so don't really mind the detail of this. The idea is that if we have a strength, we can tune the strength of the error. Then we can extrapolate to zero error. So the idea is you do measurement, you perform your quantum computation, and with result that had really bad error, slightly lower error, and then you extrapolate to zero. So do some extrapolation to zero error. And that will be your result. So I think that's a thing that people already implemented. Another thing that we were also involved is measurement, because at the end, you read out 0, 1 outcome. It turns out that actually there are a lot of errors. The way to do that is you characterize some readout, and you do something we call detector tomography, that you can extract a matrix. That matrix relate measure distribution. This is measure distribution to the ideal distribution. There's a matrix that can be characterized. This is by experiment. And then you can invert. So invert to find the ideal. So find P. P is the ideal distribution. Invert that is inverse of measured. And that could also improve your outcome. Okay, so I guess that's what I have for today. Any questions? Okay, no question. Then I'll see you guys on Wednesday.
Thank you.
Thank you.
Thank you.
Thanks.